Good morning, students. So, in this lecture, we will study transportation problem and learn various methods to find the initial basic feasible solution. Now, what is a transportation problem? Okay, so transportation problems deal with transportation of a homogeneous product from different supply centers to different demand centers. The objective is to transport all the products or material from different supply centers to different demand centers at minimum possible cost. So this is generally the objective of transportation problem. Now, what are the underlying assumptions of transportation model? Okay, the total availability at different sources should be equal to total demand at different destinations. Okay, the items can be transported from all sources to all destinations, means there is no bottleneck. The transportation is easy and it can be done. The unit transportation cost of the item from all sources to all destinations is certainly and precisely known, right? Assumptions continued here, and the transportation cost on a given route is directly proportional to the number of units shipped on that route. What does this mean, directly proportional? Means if the cost of transporting one unit is rupees 10 on a particular route and we transport suppose 20 units, then it will directly be multiplied with that per unit cost, that is 10, and so the total cost now would be 200 rupees, right? So that means proportionality. The objective is to minimize the total transportation cost for the organization as a whole and not for the individual supply and demand centers. So here in transportation problem, okay, the objective is to minimize the total transportation cost for the organization. It's not just like individual supply and demand centers. Now, mathematical formulation of transportation problem. Before formulating the transportation problem, we must understand the transportation table. Okay, so in this table we can put all the supplies, demand values, as well as the underlying per unit cost, transportation costs. So suppose we have M supply centers, okay, and at these supply centers we have supplies. At first demand supply center we have supply A1, at second supply center we have supply A2 units, then A3 units at third, and at ith supply center the supply is AI and mth AM. Similarly, we can have this demands. Okay, so first demand center we have demand B1, at second demand center we have demand B2, at 3 it is B3. For jth demand center the demand is BJ, and for nth it is BN. Okay, now coming inside the table, here C11, C12, C13, C1J, C1N, similarly proceeding, and I'm talking about IAth1, CI1, CI2, CI3, CIG, CIN, and lastly CM1, CM2, CM3, CMG, and CMN. All these are per unit costs of transportation from different supply centers to different demand centers. For example, if I talk about CIG, so it is the per unit cost of transportation from ith supply centers to jth demand center. Okay. Now, what are these values? X11, X12, X13, and so on, Xij and Xmn. Now, X11, these values, suppose I have to interpret the Xij. Okay. So, Xij will denote or denotes the amount of material transported from ith supply center to jth demand center. Okay, so this is material transported, Xij values. Okay, so this constitutes my whole transportation table, and as mentioned in the assumptions, this sum of A1, A2 and up to AM should be equal to sum of B1, B2 up to Bn. Okay, only then the this transportation problem will have unique solution. That is, the problem must be balanced one. Total supply should be equal to total demand. Okay. So after learning this table, now we can go ahead to formulate mathematically the transportation problem. Okay. Let there are m sources and n destinations. The demand at jth destination be Vj and the supply at ith source be Ai, where I from 1 to m and j from 1 to n. Let Cij denotes the per unit cost of transportation from ith supply center to jth demand center. Also, Xij denotes the amount of material transported from ith source to jth destination. Okay, so this I have already talked when we were discussing the transportation table also. Now we have defined the decision variable as well different type of costs. Okay, so now the transportation problem can be modeled as, how can we do it? So our objective function, let's say it is z is equal to summation I from 1 to m, j from 1 to n, Cij, Xij. And what we want to do for this z, we want to minimize it. We want to minimize the total transportation cost involved. Now this right hand side is giving me the total transportation cost. Okay. For example, C11, X11, then summation means plus C12, X12 plus C13, X13 and so on up to CMN into XMN. So this summation gives me the sum of all the transportation costs involved, right? So this is the total transportation cost. Suppose then it is subject to certain constraints. What are the constraints? Likewise, okay, yeah. So this first type of constraints are supply constraints, and second type of constraints are demand constraints. Okay, so summation j from 1 to n Xij is equal to Ai, where I from 1 to n m. What does this mean? That you cannot transport more than Ai to ith to any of the j demand centers. Okay, to all the j demand centers. For example, if you put I equal to 1, What does this mean? A1 is equal to summation j from 1 to n x1j. Then this sum x1j means j from 1 to n. So x11 plus x12 plus x13 and so on plus x1n is exactly equal to AI. Means the material which is being taken or supplied from supply center AI, okay, that is exactly equal to whatever is transported to all the demand centers. Material transported to all the demand centers, meaning thereby that one cannot transport more than the material available at ith supply center. Similarly, we can have this I from 1 to m x1j is equal to bj. Okay, so whatever is the demand, okay, so that has to be fulfilled. We can interpret it in the similar fashion, okay, that at every destination or demand center, the material transported must be equal to the material demanded, that is bj, and where xij greater than equal to 0. That is, we cannot transport negative amount of materials. These constraints will be consistent, that is, they will have a solution, unique solution, if I from 1 to summation I from 1 to m ai is equal to summation j from 1 to n bj. That is, total demand should be equal to total supply. We call such kind of problems as balanced transportation problems. Now coming to feasible solution, a feasible solution to a transportation problem is said to be basic feasible solution if it contains no more than m plus n minus 1 non-negative allocations, where m is the number of rows and n is the number of columns in transportation problem. So what does this mean? Okay, so you sum up the number of rows and columns and subtract 1. If we have this much m plus n minus 1 occupied cells or transportations or allocations in the transportation table, we say that the solution is basic feasible. If that contains less than these cells, m plus n minus 1, we say that the transportation problem has degenerate solution. Okay, so that is, there is degeneracy, right? So likewise, yes, then yes, again it is the necessary and transportation, necessary and sufficient condition for a transportation problem to be consistent, that is to have a feasible solution, is summation over ai is equal to summation over a bj, that is total supply should be equal to total demand. It is a necessary and sufficient condition for any transportation problem. Okay, suppose that this is not equal, in that case the transportation problem is unbalanced, and before solving them we have to make them balanced either by adding dummy supply centers or dummy demand centers. Okay, only then we can solve them. Now coming to the methods of obtaining initial basic feasible solution or solutions. First and easiest one method is northwest corner method or northwest corner rule. So here, what was original table? This was the table. Suppose, yeah, let this is the table, that this consists of C112, C123, C1311, C14, 7, and similarly. So the numbers put inside this corner, okay, these denote the CIG values, that is per unit cost of transportation. Okay, these are per unit cost of transportation, and this we have to do. Okay, the materials, the numbers put under circles denote the allocations or transportations done. But initially we don't have these values inside the circles. We have only this table consisting of these values, cost values, and the supply and demand, like 6, 1, 10, 7, 5, 3, 2. So these are the supplies and demand. So let us check first whether the total supply is equal to total demand. 6 plus 1, 7, and 7 plus 10, 17. Similarly, 7 plus 5, 12, and 3, 15, plus 2, 17. So this is balanced transportation problem. Okay. Now, what we have to do? We have to do the transportation. We have to obtain the initial basic feasible solution. For that, start from the northwest cornered cell. So this is the northwest corner cell. Okay. North this side, south this side, east this side, and west this side. Okay. So in that case, it becomes the northwest corner cell. Now transport as much as you can to this cell. Okay. So how much can I transport? That is only maximum of 7 units, because 7 unit is the total demand at this first demand center. Okay, so take the minimum of availability and demand, or supply or demand, at first supply center as well as first demand center, that is 6 and 7. So minimum of 6 and 7 is 6. Minimum of 6 and 7 is 6, that is, so this 6 will be allocated. Okay, and this is justified also, because only 6 units are available. We cannot take 7 units from there. So all the 6 units are transported at the rate of 2 to the first demand center, and still 1 unit of demand left. So I put 1 here, right? That coming to, I cannot go in the first row now, because this total demand is supply is exhausted. Now going to the second row, because there is some supply available at supply center 2. Okay, so now in this cell, take the minimum of supply and demand at supply center 2 and demand center 1. That is, here 1 is demanded and 1 is available. So these values are equal. So put this value here. Okay, there is no point of minimum, because 1 is required and 1 is available, and these values are equal. So put 1 over here. So that is, 1 unit is transported from supply center 2 to demand center 1 at the rate of 1. Now this supply is exhausted and demand is also exhausted at this. Now we will have to move to the third row. Okay, and in third row also to the second column. Okay, because here nothing is demanded. So coming to here, now what is the supply and demand? 5 is demand and 10 available. So take the minimum of 5 and 10. So that is 5, and 5 units are transported at the rate of 8 to this, that is to demand center 2 from supply center 3, right? So yes, so by taking the minimum of 5 or 10, what does this mean? That is 5 units were demanded, so all those 5 units are taken from here, right? So 5 left. Then again we will have to do the transportation only from third supply center only, because the supply at first and second is exhausted, and the demands are still left. So coming to the demand center 3, here 3 units are demanded and 5 left with supply center 3. So take the minimum of 5 and 3, that is 3. So take all 3 units from here to here. So I put 3 here and put this 3 inside the circle. It means the transportation or allocation done. Now again 2 units, 3 units taken, so 2 left, okay, and again 2 units are left or required at supply center 4. So the minimum of, sorry, 2 and 2, that is these 2 are equal and 2 are demanded, 2 are left. So put these 2 units at this point in this cell. Okay, so this way all the supplies are finished and all the demands are also satisfied, and hence the initial solution is obtained. Let us check whether it is initial basic feasible. So it is feasible already, and not let us count what is the number of rows, 3, and number of columns, 4. So 3 plus 4 7, and 3 plus 7 minus 1 6, and plus and minus 1. So there should be 6 occupied cells in order this solution to be basic feasible. Let's count 1 2 3 4 5. So this solution is not initial, this is not basic feasible, it is degenerate one, okay, but it is initial solution, okay. And these are the cases, sometimes we get this type of solution, and this can be handled, okay. Now coming to the second method, okay, the solution is the initial solution from this 1 2 3 4 5, yeah. So initial solution obtained using this northwest corner rule is just like x1 is equal to 6, x2 is equal to 1, x3 2 is equal to 5, x3 3 is equal to 6, and x3 4 is equal to 2. That is this one, okay. And we can also compute the transportation cost involved by just summing these products, 6 into 2 plus 1 into 1 plus 8 into 5 plus 15 into 3 plus 2 into 9, okay. Now coming to the second method, that is least cost method, or matrix minima, or lowest cost entry method. So in this method what we do, we select the lowest cost throughout the table, okay. So what is the lowest cost throughout the table here? That is 0. So the cell having least cost is selected for transportation, okay. So what is the supply here corresponding to this 1, and what is the demand corresponding to this? That is 5. So what is transport as much as you can to this cell, okay. So what is the maximum availability? That is 1. So I cannot transport more than 1. So the minimum of 5 and 1, that is 1, is transported here. So 1 is put here. Now coming, now this supply at this center is exhausted. That is, this will not be considered for transportation further. Now coming to the next lowest transportation cost, that is 1. but it lies in this row, so this is not possible. It's not possible to select this cell with one cost as the supply is exhausted, finished. So the remaining table is like this: second, first row and third row. From this we can see that the lowest cost is 2. So transport as much as here. So take the minimum of 6 and 7, that is 6 is transported here, allocated here, and nothing is left with this supply center. So I put 6 here now. Okay. Now I cannot consider this row and this row for finding the lowest costs because here the supplies are finished. So now I have to move to the only third. So these no shades are only added just to understand or just to show that don't consider these first and second rows for transportation. Now going to the third row here. Okay, what is the minimum cost? 1. No, it's 5. 5. So allocate as much as you can to it. So here 1 is demanded and 10 is available, minimum of 1 and 10 is 1. So 1 unit is transported here at the rate of 5. So now the total demand is finished. I put cross here. And going to the next row, okay, because 4 units are still left with D2, demand center 2, as 1 is already transported to it. So take the minimum of 4 and 9, that is 4. Okay, so 4 units are allocated here. Now how much left? 5 is left. Okay, again move to the next, that is 9 here. 15 and 9, minimum of 15 and 9 is 9. So select this for transportation. 2 are demanded and 5 left. Okay, so you transport 2 here, 3 left, and after that put those 3 here, or there is no need of finding the minimum cost here because only 3 and 2 are demanded and 5 left, so there is no other choice. We will have to take the material from this third supply center, and obviously 3 have to be transported only from here and 2 have to be transported only from here. So put 3 and 2 over here. Okay, this way this I can put a cross over here. Okay, I have not put, so this is also satisfied, exhausted. Okay, so what is now my solution? That is only this: 1 2 3 4 5 6. So here are 6 allocations, same type of transportation as was available with northwest corner rule, but this method we are getting 6 allocations, m plus n minus 1. So this solution given by least cost method now is basic feasible solution although it is initial solution. So what is the solution? x1 1 is equal to 6, x2 2 is equal to 1, x3 1 is equal to 1, x3 2 is equal to 4, x3 3 is equal to 3, and x3 4 is equal to 2. And here these are empty cells. This is empty cells, empty cells, empty cell, empty cell. Nothing is transported in these positions. Okay, so this is only my solution. I have just written what I have spoken here. Okay, so you can read here. From here select the least cost cell. Here it is 2 2 having cost 0, then allocate minimum of this 1 there, then go to next lowest cost cell. We have 2 such cells. In such case choose arbitrarily anyone, but since the availability test is exhausted, so this will not be considered for allocation. Next cell is this one, and having this minimum of 6 and 10 is 6, so that is 6 will be allocated there. Next lowest cost cell is C31 is 5, having cost 5, and minimum of 1 and 10 is put over there 1. Next lowest cost is this, and this we continue, and this is minimum 4 and 9, that's 4. Next is 3 4, allocate minimum of 3 5, that is 3, And lastly, 2 left with S3 and 2 required at D4. So allocate 2 units at cell 3, 4. So this way, this lowest cost method work. Finally, the solution, as I discussed, is like this. These are the values, and the cost obtained jet, total cost of transportation initially, that is 11,200. Now we can go to the third one, Vogel's approximation method. Okay, we call it like Vogel's approximation method, VM. Okay, what we do in this, okay, this is again same transportation table as we have started with northwest corner rule and least cost method. So this is the cost structure, and this is demand, supply and demand. Okay, with this. So in transportation matrix or transportation table, if an allocation is made in the second lowest cost cell instead of lowest, okay, so suppose if we do the transportation to the second lowest cost cell instead of lowest, then what happens? Then this allocation will have a penalty associated corresponding to the difference of these two costs due to loss of advantage. That is, if we compute the difference between two lowest costs for each row and column, we find opportunity cost relevant to each row and column. It would be most economical to make allocation against the row and column with highest opportunity cost. For a given row or column, the allocation should obviously be made in the least cost cell of that row and column. What does this mean? What is the meaning of what I read? Okay, so suppose let us see this table, and let us find out the difference between the lowest and the next lower cost. So here in the first row, what is the lowest cost? It is 2, and next lower it is 3. So 3 minus 2, 1. This 1. Similarly, the second, 1, 0. 1 minus 0, 1. Third, 5, 9, 5, 8. So 8 minus 5, 3. Similarly for columns, that is 2, 1, 1. 3, 0. 3 minus 0, 3. 6, 11. 11 minus 6, 5. 7, 1. 7 minus 1, 6. So these are the differences along columns and along rows for this table between the next lower and lowest costs. So suppose instead of allocating to this lowest cost cell, we allocate to this one next lower cost, okay, then we are losing an opportunity to allocate to transport with the minimum transportation cost. Okay, if I select this first row for doing the transportations, okay, that is I am facing some penalty of difference between 3 minus 2, that is 1. That is 1 unit, 1 per unit I have to pay more for transportation. Okay, understood? Similarly, I can go for the any column, let us say third column. So here it is 6 and 11. 6 lowest, 11 next lower. So it is 5. So if instead of transporting to this cell, we are having the least cost, lowest cost, I transport to the next lower, that is this cell here, having transportation cost 11. So what is the penalty to me? That is 11 minus 6, that is 5. 5 units per unit I have to pay more for transportation. So that's why this method is also known as penalty method, and we take into consideration all this. And yes, what we do then, we compute the penalties across rows and columns and select the row or column having highest penalty, because we want to avoid that kind of transportation which involve highest penalty first. Okay, so select the row and column having highest difference or penalty, that is here in this first computations. Here it is 6. So select the particular row and column corresponding to this, that is it corresponds to fourth column. So I selected it, and now select the lowest cost cell here for transportation, that is 1. It is 1. So I selected this, and I transported minimum of 1 and 2 here, that is 1 is put here. So now what happens, supply at this is finished, that is why I have shaded this one first. So we will not consider this for computation, this row for computation of penalties next. Okay, so this is I put here dash, the penalties are like this: 1 3 3 5 4 2. Okay, same way we found it. Then what is the highest, that is 5, and select this second column now for transportation. So in the second column and in the first and third row, the lowest cost is 3. So transport as much, so minimum of 5 and 6, that is 5. So 5 is put here and 1 left over here, and 5 is satisfied. This is finished. So now we will not consider this for further computation of penalties. Third time again we find out penalties. So these are 5 4 2 4 3. Which one? Here it is highest. So 5. Go to the first. Yes, because 1 is left here. So go to the first row and select the minimum cost. That is 2 here, because we will not consider this. So 2 here, as allocate as much. So minimum of 1 and 6 is 1. So 1 is put over here, and this supply is exhausted. Yes, supply exhausted, and yes. So yes. So 6 are sorry 7, and minimum of 7 and 1. That is 1, and 7 minus 1, 6 is left over here. Now what is the case now? This and this row will not be considered. So we have now only one choice, that transport to the remaining demand centers only from supply center 3. Okay, so what is to be done now? So yes, go find out next time this kind of things. Okay, so it is 4. The difference is 4 is highest, so it corresponds to this column also, and it corresponds to this row also. So selecting this row, arbitrarily we have a choice, we can select anyone. I am selecting this row. So yes, 6 are in this particular row. This 5 is minimum cost. So yeah, so 6 units, take the minimum of 6 and 10, that is 6, and put 6 over here. Now all the demand in this D1 is finished, and this is already I think finished. Yes, and now coming to this one here, 3 are demanded, and yes, coming to this, yes, now we have no other choices, only this 3 and 2. Okay, so suppose if I, yes, what happened was, yes, one is already, yes, one was left over here. Yes, right. So one unit is transported from here to this, and 3 units are transported from here to this one, because there was no other choice. So that's why in this way this is done. Otherwise you can also do this differences. There is no need of finding differences, even because only this one row is left for computing the differences and all this. So 3, put 3, remaining 3 over here, and 1 over here, so that all the supplies are finished and all the demands are also satisfied. And hence this way I got the initial solution 1 2 3, 4, 5, 6. Again, here are 6 allocations, and again, this is initial basic feature solution. So this is the solution x111, x125, and likewise x341. So what is the transportation cost? That is 10,200. It's found that this Vogel's approximation method provides us the minimum transportation cost as compared to the northwest corner rule and the least cost method. So most of the times we start with the Vogel's approximation method, and sometimes it also provides the optimal solution or near optimal solution. Okay. So thank you very much for your patience listening. Yeah. Okay.